These are the lesson activities for section 3.1. Okay, definition. A lower triangular matrix is a matrix with all zeros below the main diagonal, and an upper triangular matrix is a matrix with all zeros above the main diagonal. So we're supposed to create a 3 by 3 lower or upper triangular matrix with numerical entries of your choice. So 3 by 3, and I'll make a lower triangular matrix. So I'm going to put like that. So zeros below the main diagonal. Then I'm just going to put random 1, 2, 3, 4, 5, 6. All right, so for that 3 by 3 triangular matrix, we want to calculate the determinant using a cofactor expansion. So the easiest expansion to do would be across the bottom row because of the 2 zeros, or the first column, whichever one you prefer. They both have 2 zeros. I actually am going to do the first column because that 1 makes things nice and easy. So I'm going to do a cofactor expansion down the first column. So the way you do that is we start with the 1. We're going to work our way down this column. So you start with the 1. And you're going to have 1 times the determinant of a 2 by 2 matrix that is left when you cross out the row and column of that 1. So that would be 4, 5, 0, 6. Okay, then you could proceed down the column. So you would do plus, actually it would be minus 0 times the 2 by 2, which doesn't matter, plus 0 times 2 by 2, doesn't even matter what's in there. Okay, so this is going to be 1 times the determinant of 4, 5, 0, 6 is 1 over AD minus BC. I'm sorry, it's just AD minus BC. I was thinking of finding the inverse, just the determinant. AD minus BC, so that's 4 times 6 minus 5 times 0, which is 24. All right, so now it says multiply the diagonal entries of your matrix together. So my original matrix, diagonal entries, 1 times 4 times 6 is 24. Oh, hey, that's the same as I got up there. Same as the determinant. So your conclusion from part 1, our conclusion is that the determinant of a triangular matrix can be calculated by multiplying the diagonal entries together. So the determinant of a triangular, whether upper or lower, is the product of the diagonal entries. Okay, so now I have a 4 by 4 matrix, and I want to calculate its determinant using a cofactor expansion. So I'm definitely going to go down the third column because it has 3 zeros. So I'm going to do, it's the third column, so you start with the 2, not changing the sign, and then you're going to calculate the determinant of the 3 by 3 matrix that's left when you cross out the row and column that contains that 2. So what I'm left is 0, 3, negative 4, negative 5, negative 8, 3, and 0, 5, negative 6. All right, that is a 3 by 3 determinant. I'm going to have to do a cofactor expansion on that to figure out its determinant. I think, again, I'm going to go down the first row. I'm going to go down the first row this time because it has 2 zeros. So this is going to be 2, and then we'll put a big bracket while I'm working on this. So the 2 is times the final result of what I get here. So it would be 0 times a 2 by 2 determinant. I'm not even going to bother writing that down because it doesn't matter. And then I'm going to change the sign. So this is going to become plus 5 times the 2 by 2 that's left when you cross out the row and column. And you get 3, -4, 5, -6. And then plus 0 times another 2 by 2. So this is 2 times 5 times AD minus BC. 3 times -6 minus -4 times 5. Okay, so that's -18 plus 20. So that's 2 times 5 times 2. 2 times 10 is 20. Okay, so we're going to let u be the vector 3, 0, and v be the vector 1, 2. And we're supposed to draw the parallelogram determined by u, v, u plus v, and 0. All right, so 0, the 0 vector is just a point at 0, 0. Then I have 3, 0, which is right here. 1, 2, which is here. And then u plus v is 4, 2. Add them component-wise. So now we'll plot 4, 2, which is here. So I'm going to draw that vector. And that creates a parallelogram if I connect the dots here. All right, so now we're supposed to compute the area of this parallelogram. The area of a parallelogram is base times height, just like a rectangle. And height is the perpendicular height between the parallel sides. So my base would be this, which is 3. And the height would be like that, which is 2. So 3 times 2 is 6 for the area. And then we're supposed to compute the determinant of a matrix where the columns are u and v, and then another one v and u. Okay, so I want to calculate the determinant of the matrix 3, 0, 1, 2. So that would be 3 times 2 minus 1 times 0, which is 6. And then separately, I'm going to calculate the determinant of VU. So I'm going to switch the columns 1, 2, 3, 0, which would be 1 times 0 minus 3 times 2, which is -6. Okay. So how do the area of the parallelogram and the determinants compare? They are equal or opposite, right? So the area was 6, and the area will always be positive. So the area, the area is equal to the absolute value of the determinant of the matrix. Okay, I've got a matrix A, 3, 1, 4, 2, and I want to calculate 5A. So that means multiply every entry in the matrix by 5. So that would be 15, 5, 20, 10. Okay, so the determinant of A, that's 3 times 2 minus 1 times 4, which is 2. The determinant of 5 times A, so 15 times 10 minus 5 times 20. 150 minus 100 is 50. Okay, so is the determinant of 5A equal to 5 times the determinant of A? So the determinant of 5A, that's 50. 5 times the determinant of A, that's 5 times 2. Those are not equal. But we're supposed to write an equation that does relate the determinant of 5A to 5 and the determinant of A. And what I can do is I could say, well, 50, it's not equal to 5 times 2, but it's equal to 5 squared times 2. So that means that the determinant of 5A is equal to 5 squared times the determinant of A. Interesting. If ABCD is a matrix A and K is a scalar, we're supposed to conjecture a formula based on the results from earlier parts of this problem that results the determinant of KA to K and determinant of A. Okay, so I think that the determinant of KA is going to be K squared times the determinant of A. Because in the example we did, the K was a 5. We had to square it to make it equal. So for an extra challenge, prove your conjecture. I'm going to leave that to you. Okay, here's a matrix 1, 2, 3, 4. Calculate the determinant of A. So that's 1 times 4 minus 2 times 3, which is negative 2. All right, on the matrix A, we're going to perform the row operation. Row 1 becomes 3 times row 1. And the resulting matrix we're going to call A prime. So A prime is going to be, I'm just replacing row 1 with 3 times row 1. So this is going to become 3, 6, 3, 4. Okay, calculate the determinant of A prime. So that would be 3 times 4 minus 6 times 3. 12 minus 18 is negative 6. Write an expression that relates the determinant of A to the determinant of A prime. Okay, so the determinant of A is negative 2. The determinant of A prime is negative 6. So that means that the determinant of A, if you multiply it by 3, you get the determinant of A prime. And how is that related to the row operation performed? I scaled a row by 3. And that scaled the determinant also by 3.